on the elimination half-life, elimination rate constant, and absorption rate constant. On what factors does the Ka, the absorption rate constant, depend? Depends on the route of administration, the dosage form, and the formulation, right? Okay, so these are the factors that define absorption rate constant. What about the elimination rate constant? If you have a linear pharmacokinetic, the elimination rate constant should be what? Should be dose independent, time independent, concentration dependent, right? That's for the elimination rate constant. What changes the elimination rate constant? If the patient receives an inducer or an inhibitor, or the patient develops certain hepatic disease, for example, or renal disease. These kind of diseases, they can modify the elimination rate constant. Any modification in these two parameters that can modify what? The Tmax. Now, once you get the Tmax, how to get the Cmax? Simply, you plug in the value of the Tmax where in the equation for the concentration in plasma. So you substitute the T by Tmax. That's how you get the Cp max. So if I ask you an exam, what's the Cp max? You have to do two steps of calculation. The first step to get the Tmax, okay, and the second step to get the Cp max by plugging the value of the Tmax in this equation. And as I mentioned, if I change the dose, Tmax will not be modified, right? Whereas the Cp max will be modified if I change the dose. Does the Cp max depend on the dose? Look on the equation, right? It has a dose, right? So if the dose increases, then this whole intercept, the capital, what we call the capital A, will increase. Well, that means that the Cp max will also increase, right? Right? The Tmax will not be affected by the changing or the change in the dose. Tamam? Any questions? Based on this graph here, which one has a faster absorption? The continuous line or the dashed line? Faster absorption. The continuous. Why? Because its Tmax is earlier. This is the Tmax 1, and this is the Tmax 2. So the continuous line has an earlier Tmax, which means it has a faster absorption compared to what? To the dashed line. Okay? These could be two different formulations, or two different dosage forms, or two different routes of administration for the same drug. Okay? Because all of these can modify the what? Absorption rate constant. Tamam? Any questions now? Okay, so what about if I increase the elimination rate constant? What will happen? What if I increase the elimination rate constant and keep every other parameter the same? What will happen to the Tmax, for example? We agreed that the elimination rate constant affects the Tmax, right? So if you have a larger elimination rate constant, what will happen to the peak? Will it be earlier or it will be delayed? It will be earlier. Why? Okay, what does that mean? If you go to the definition, if you have a faster emission, okay, represented by larger value of elimination rate constant, the point where these will be equal, the rate of input and the rate of elimination will be earlier. Okay, so the peak will be lower or will be higher? Will be lower. Makes sense, right? If you have a faster elimination, then your peak will be lower, right? Now let's go to what if I increase the absorption rate constant? Again, the point where they will be equal will be earlier, so the peak will be earlier, right? So the peak will be earlier if I increase the absorption rate constant. But the peak will be higher or lower? If I increase the absorption rate constant, it will be higher, right? If I have a faster absorption, the peak will be higher, right? Now, what if I change the dose? What if I increase the dose? Will the Tmax will be affected? The Tmax will be the same. What about the Cp max? it will be changed, right? Because on this relationship, if I increase it, if I double, for example, the dose from 10 to 20, the CP max should be doubled, right? مظبوط? Okay, so what are the parameters that we can use to characterize the concentration time profile? Or this is the concentration time profile after extravascular dosing. Okay, the first parameter is Tmax. Is it representative of the rate or the extent of absorption? It is an indication of the rate. If you have a shorter Tmax, you will have a faster absorption, right? What about the CP max? It's both. It's the rate and the exit. Okay. If you, as we mentioned before, if you have a faster absorption, CP max will be higher, right? So it's a measure of the rate. And what about the extent? If you have a higher bioavailability, go back to the equation, which is a measure of the extent. Okay. If you have a larger value of F, then you will have a higher CP max. So also CP max is a measure of the extent, right? So CP max is a measure of both rate and extent. T max is a measure of the rate. And we have the third parameter, which is the area under the curve. This is the shaded area under the curve. Okay, it's a measure of what? Extent. So you have one parameter for the extent, that's the area under the curve. One parameter for the rate, that's the T max, and one parameter for both, which is the C max. You got it? Any questions in now? Anything that's not clear? Okay. Now, as a summary, if I have a linear pharmacokinetic, okay, linear pharmacokinetic, if I change the dose, okay, what should be the same? Only the dose. But the route is the same, the formulation is the same, and the dosage form is the same. I change only the strength from, for example, 5 milligrams to 10 milligrams. What should be dose independent? Tmax, also. The dispersion parameters, which are the K, will VD, will clearance, will half-life, and also the Ka and the F, the absorption parameters, also they should be dose independent, because if you have linear absorption, they shouldn't vary by changing the dose. That's the what? The Ka and the F. Okay. What can be changed by changing the dose? As we mentioned before, if I increase the dose, what happened? The CP max was increased, and the CP at any time point was increased. What about the area under the curve? Also, right? Because the area under the curve from 0 to infinity is equal to F multiplied with the dose divided by the clearance. So if you change the dose, the area under the curve will change. Every time I ask you such a question, and remember or look for the equation that represent the parameters that I'm asking for, right? And you make your decision based on the analysis on that equation. Any questions till now? Right. Let's go to the first example. We have drug X, which was administered at 500 milligrams. Drug X that is excreted unchanged and completely absorbed. When I change it from completely absorbed to completely bioavailable. Just scratch this word here. So this is not completely absorbed. Completely absorbed means that F absorbed is equal to 1, right? But this is completely bioavailable. So replace absorbed by bioavailable. That means that bioavailability is equal to 100%, right? But completely absorbed means that F absorbed only is equal to 1, not the net multiplication of the 3 parameters. Tamam? Now we have the data, we have the time, and we have the concentration. This is the regular data that you have, right? Now, we need to do 2 steps of calculation as we saw before. We need to do an estimation for the elimination rate constant and the intercept, okay? And then using the method of feathering or the method of residuals, we get the value of what? Of the residuals, from which we can get the absorption rate constant. So there's a major assumption that we are making is what? Which is larger, the Ka or the K? If you have a normal kinetics, okay, then the Ka is much larger than the K, which means that the slower process is what? Is the elimination, which means that the terminal slope here is relevant to what? To the elimination. This is what I explained the last time. Okay, as I mentioned before, and you are required to, and at least to listen to the previous class or read it before you come to the next class. Come on. So The initial rate constant is relevant to what? To the terminal slope because it's the slower process. تمام? And what about the absorption rate constant? It's relevant to the residual line. تمام? Because it's the faster process. Which one has a higher slope? The residual line, which is this one, or the elimination rate, or the elimination phase line? This one has a higher slope, right? As we mentioned before, we are making the assumption Ka is larger than the K. So the Ka will be related to the faster slope, right? Which is the residual line. If we have flip-flop kinetic, on the other hand, it will be the other way around. The flip-flop kinetic means that the Ka is much lower than the K. So the slower process is what? The Ka. So the terminal slope will be relevant to the slower process, which will be in this case what? The terminal slope will be of the elimination phase, or let's say the post-distribution phase, let's call it, will be relevant to the Ka, and the residual line slope will be relevant to the K, right? So we do linear regression first on the elimination phase. So as we mentioned before, at least we need to do it on 3 time points. Okay, we take the last 3 time points. We do linear regression of that. Do we do the linear regression of the data as is? What's the equation for the terminal phase? That's Cp prime equal to A multiply with e power minus k Ft. Is this a linear equation? It's not, right? So can we do linear regression on it as it is? We need to take the natural log or the log, right? So we need to take the natural log or log of this column here, which is the Cp prime, okay? And then do linear regression on that. From that, we can get the intercept, okay, and the K, which is relevant to the slope, right? Once we do that, we know the parameters, which are the A, the capital A, and the K, right? This is the first step. The second step is to do the linear regression on the residuals. Do we have residuals in the original data? The answer is not, or no. So this is the original data. We have time here. This is time. This is Cp. And we do the method of residuals on the absorption phase, right? So this is time again, and this is Cp. Observe, right? Now we have a further step to do is what? To calculate the back extrapolated part, right? Which is this part. Now this part, shaded in yellow, can be described by the same equation of Cp prime, right? مظبوط? So basically, I will go for T1, which is this one, equal to 0.5 hours, and plug it in this equation, Cp prime, to get Cp prime at time equal to Gadesh to 0.5. And I will do this at 1 and 2 and 4 hours, right? I'll do this in which phase? In the absorption phase, which is this phase, right? Because I'll do it here. So this is the absorption phase. So I calculated the back extrapolated values, which is the extension of the terminal phase, right? طيب. And the next step شو كانت؟ إنه أخذ الفرق بين or take the difference between the Cp prime, which is this one. Now we have Cp prime here that we just calculated using this equation, right? And we did that, as I mentioned, in the absorption phase. So we did it. We need to do it again on at least 3 time points, because linear regression need to be done on at least 3 time points, right? You cannot do it in 2 time points, as we mentioned before. So I'll do it in the absorption phase. Okay, I'll calculate Cp prime using this equation here at these time points by just plugging the value of the t. And all of that you need is to plug the values of these t's, okay, in this equation, right? Now you have the values of the Cp prime. And the last step is the residual, okay, calculation, which is equal to Cp prime minus Cp, right? This is the fourth column. This is Cp prime minus Cp. Right? Why do we do this? Because going back to the method of residuals, and we have read this. This is the equation of Cp prime. This is the equation of the Cp, right? We just take the difference between them. This is Cp prime, A multiplied with e power minus k Ft, while Cp is equal to A multiplied with e power minus k Ft minus e power minus Ka phi t, right? So the one in red are the same, right? So when you take the difference between these two equations, what will happen? They will cancel out, right? And then you have minus minus here. That's equivalent to what? Positive. So the difference between them, which is equal to the residual, which is this relationship here, is equal to what? Equal to A multiplied e to the minus Ka multiplied with T, right? So this is the residual, right? Does it have elimination parameters? Does not, right? So it only has Ka. So if you do linear regression on the residual, you'll get the what? The Ka. Again, do you do linear regression on the residual as it is? Guess what? It's an exponential relationship. You have to do it on the natural log or the log. So you have to linearize the equation first or the data, and then you take or you do the linear regression. Okay? We do this in which phase we said? In the absorption phase, not in the elimination phase. So this is assuming linear, or this is assuming normal kinetics, whereas the Ka is larger than the K. If you have flip-flop kinetic, okay, as I mentioned before, the terminal slope will be relevant to what? To the Ka, right? Because it's the slower process, and the residual line slope will be relevant to what? K. Okay, please go back and review the previous course or previous class. Going back to our table here, so we calculated the Cp prime first by just plugging the values of the t's in this equation of Cp prime, and then we took the difference between Cp prime minus Cp. Why do we take this? Because which one is larger, the Cp prime or the Cp? These are the Cp's, right? And the Cp primes are these. Which is larger? The Cp prime, right? That's why we take Cp prime minus Cp. That will give us the what? The residual. As I mentioned, the residual is not a straight line equation. It's what? It's an exponential. So we have to take an additional step here. What? And this is, as I mentioned, this is the residual. You have to take the natural log of residual, right? And then you do linear regression on what? Natural log of residuals as a function of time. That way you can get the what? The absorption. You got it? This is just a review for the method of residuals which we covered in the last class. Right. Hello, which means you try to get the value of the, you remember how to get the half-life, right? The half-life definition is what? It's the time needed for the amount of concentration to go to half its value, right? And for example, if I look at the elimination phase here, I will look the time that's needed for the drug concentration to drop from 10 to 5. Okay? That will give me the elimination half-life, right? Because the terminal phase is relevant to what? To the elimination in our case, because we have normal kinetics. So the elimination half-life is equal to get this 10 hours, right? Which means that the K is equal to 0.693 divided by the half-life, divided by 10. That will give us a K of 0.07, right? What about the residual line half-life? Indicative of what? Which half-life? Elimination half-life or absorption half-life? Absorption half-life, right? Because in our case we have normal kinetics, so the residual line slope here is relevant to the absorption half-life, which came to be 2.8 hours. That's the absorption half-life, which means that the absorption rate constant is equal to 0.693 divided by the absorption half-life, 2.8 hours. That will give us an absorption rate constant equal to 0.247 per hour. And remember, the units for rate constant, first order rate constant is what? Per time, right? Per hour here and per hour here. For the elimination rate constant and the absorption rate constant. Now, also, upon extrapolating the values, we found what's the intercept, which is the capital A, right? That was found to be 67 milligrams per liter. So this is this intercept. So this intercept here is equal to 67 milligrams per liter. How can I use the intercept? I can use it to get the what? The VD over F. So the VD over F is equal to dose multiplied with Ka divided by intercept, which is the capital A, multiplied with Ka minus K, right? So the dose is 500 milligrams. The Ka, we calculated that to be 0.247. The intercept is 67, and the K is 0.07. If you do this, you can get the value of Vd over F, right? Now it was, or we were informed in the exam or in the question is that the bioavailability is equal to 1. So Vd divided by 1. Okay, Vd divided by 1 is equal to 10.37 liters, which means that Vd is equal to 10.37 liters, right? Because F, the absolute bioavailability, is equal to 1, right? The last part, it's asking us to get the values of the peak time and the peak concentration. Now we know the K, we know the Ka, so we can get the Tmax, right? Tmax is equal to natural log of Ka divided by K divided by Ka minus K. So natural log of 0.247 divided by 0.07. The whole thing is divided by 0.247 minus 0.07. That will give us a Tmax equal to 7.15 hours, right? That's the Tmax. How to get the Tmax? I'll put this value of Tmax in the equation of Cp, right? Instead of the time, right? We know the K, we know the Ka, we know the Tmax, and we know the F, okay? And we know also the Vd that we just calculated, right? We know the dose, so everything is known. We can get the Cp max. One thing that you need to observe here, what I did here, as Vd divided by F, right? And I gave an exam question before where I only gave the students the value of Vd divided by F. It's the same thing, right? This is the denominator of the denominator, the F. It will go to the denominator, right? Right, and this is similar. And imagine that this F is not here, it's here, right? So I can give you the Vd divided by F without giving you the value of the F, and you can still calculate the Cp, right? Because again, imagine that this F here is not here, it's here, right? Because F is the denominator of the denominator, which means it's the what? Denominator. Right? You understand that? So even if I don't give you the value of the F, if I only give you the value of Vd divided by F, you can still do the calculation. Come on. Any questions? And again, to emphasize the concept, if I change the dose, will the Tmax change? If in this example, if I ask you to get the Cp max at a dose of 1000 rather than 500, what should you do? Right, so in this equation, the only thing that you need to change is what? The dose. Here you change the dose from 500, which is the original dose, right? To what? To 1000. Because the only thing that will change if I change the dose is the dose. F will not be modified, okay? The Ka will not be modified. The Vd over F or the Vd will not be modified also. The K will not be modified. And then Tmax, likewise, will not be modified. So the only thing that will change if I change the dose is the dose itself. And remember that this whole thing here is the what? Is what we call the capital A, right? Right? So if capital A, for example, is equal to, in this case, to 67 at a dose of 500, what will be the capital A at a dose of 1000? Huh? 5, right? Because the dose will be double. So let's call it A prime. A prime will be 2 multiplied with 67 at a dose of 1000, right? Milligrams. Or simply, the Cp max will be double this value. If this is a Cp max from 500 milligrams, okay, the dose from 1000 milligrams will be double this value, right? Why is double? Because everything between parentheses will not be changed, right? كل شيء هون بين قوسين ما راح يتغير. I change the dose. The only thing that will be changed is the what? Is the A. It will change from capital A high to capital A prime high. will be doubled, right? Why double the dose, right? Which means the CP max will be doubled. Actually, and each time points, and if I go you have this curve here. Assume this is the curve from 500 milligrams. Okay. If I have a dose, another dose of 1,000 milligrams, okay, that's in blue. Everything will be double exactly the values at any time points. Okay. Will be the double at CP max. Also will be doubled here. Will be doubled here. Will be doubled here. Because simply, if you go back to the equation, we double the dose. This is the equation, right? I double the dose. The time is the same at any time point, right? The Ka and the Ks will be the same, right? The F will be the same, the Vd will be the same. The only thing that's doubled is what? Is the dose. If you double the dose at any time points, the concentration will be doubled, including the concentration at Tmax, right? You got it? Any questions? So as we mentioned, this is the dose 500, and this is from 1,000. And the Tmax will be what? In both cases, it will be the same Tmax, right? Because Tmax is not affected by the dose. Okay, any questions? Right. Let's take or look at the second example. A single oral dose of 100 milligrams of antibiotic was given to an adult male patient who is 43 years and 72 kilograms. From the literature, the pharmacokinetics of this drug fit a one-compartment open model. شو يعني open model? يعني the drug or the process involves an elimination process, right? The equation that best fits the pharmacokinetics of the drug is this equation. Cb is equal to 45 multiplied with e to the power minus 0.17 t minus e to the power minus 0.15 multiplied with t with time, right? This is the equation. Now this is the equation from a dose of what? 100 milligrams, right? And if I change the dose again to emphasize the concept, if I change the dose from 100 to 150, for example, which parameter will be modified in this equation? The 45, which is the intercept. This is the 45, which is equivalent to what? Capital A, right? So this is the only thing that will be modified, which is equal to what? Capital A. Capital A is equal to F divided with the dose divided with Ka divided by Vd multiplied with Ka minus K. So if I change the dose, the only thing will be modified this capital A, because the F will not be modified, the Ka, the Vd, the K will not be modified also, right? We were asked to calculate what? The Tmax, the Cmax, and the elimination half-life. First, we have to make an assumption. That's an important assumption, which is right. So Ka is much larger than the K. So we have a normal kinetic or flip-flop kinetic. We have a normal kinetics, right? So we have a normal kinetic, which means based on this value, which is larger, the 0.017 or the 1.5? Which is larger? 1.5. So what's the Ka? 1.5. What's the K? 0.17, right? Which means the elimination half-life to begin with. What's the elimination half-life? It's 0.693 divided by which value? This one or this one? The elimination half-life is 0.693 divided by the K, right? So it's divided by 0.17, right? The first thing has been done. So what about the Tmax? Tmax is natural log of Ka divided by Ka minus K, right? That's the Tmax, right? Now we know that the Ka is 1.5 and the K 0.17. Just plug in the values here. That will give you a Tmax equal to 1.63 hours. Now the last step, what's the Cmax? At the same dose, which is 100. Use the same equation and put the value here of T equal to Tmax, right? What if I have a dose of 200? I'll ask you to get the Cmax. So I'll multiply this A by 2. I double the dose from 100 to 200, right? That will double the intercept A, but will not affect the K or the Ka or the Tmax, right? Got you? So as a homework for you, do the same question here, but for a dose of 250. Okay, this is a homework for you. So the original calculation here we made for 100 milligrams. Just do the calculations, but at a new dose of 250. Assume that this equation is from a dose of 100. Right? You have a question?
When do we assume we have?
We will have, we will discuss it in a minute. Yes. So the default is that you have a normal kinetics unless I stated something else in the text of the question. Okay, I said clearly that this drug has a flip-flop kinetic. Okay, how to know whether you have a normal kinetics or a flip-flop kinetic? We'll discuss this inshallah in next coming slides. تمام؟ هلا طبعا something that I keep reminding you is that this equation applies for the oral, also applies to what? Subcutaneous, intramuscular, okay, inhalation. Anything that involves an absorption, okay, you can use this equation, assuming that you have one compartment model. This question, like if rather than talking about oral dosing, we can use the same kind of calculations, even if you have another extravascular administration. The same applies also for this question. Tamam? Any extravascular administration can be treated the same. We can use the same equations. The only unique equation for oral dosing was what? Do you remember what? That equation that can only be applied for oral dosing was this equation. F is equal to F absorbed by Fg multiplied by Fh. This is the only equation that's unique for oral dosing. Every other single equation in this chapter, it is applicable for any kind of extravascular administration except this equation. Okay? Because it describes the process of oral absorption. This is the Fg, which belongs to the extraction by the GI wall, and this is the Fh, which describes the extraction by the liver, and this is the F absorption, the fraction absorbed from the where? From the GI loop. So describe the oral absorption. The process of intramuscular absorption or subcutaneous or inhalation is different. Yeah, the only well understood خلينا نحكي process of absorption is actually the oral absorption, because we know exactly what happens here, what happens here, what happens here. For the intramuscular or subcutaneous, it's a little bit different. The process can be described, at least the drug that come from, for example, subcutaneous absorption or intramuscular do not go to what? To the liver, right? There's no first pass hepatic extraction after intramuscular dosing or subcutaneous dosing or inhalation dosing. It's only applicable to what? To oral dosing. Also, there's no GI wall extraction on the first pass except after oral dosing. That's why this equation is only relevant to what? To oral absorption. The other equations in this chapter, they are general equations. They can be applied to kull or to all of the extravascular dosing routes. We have seen this example before. I think it was example 5 in the chapter by IV Wallace. Procainamide is used for the treatment of ventricular tachyarrhythmia. It is administered intravenously, orally, and intramuscularly. There we talked about the intravenous route, right? Here we talk about the oral. When a 750 milligrams dose is administered intravenously to a normal healthy subject, the relation half-life was 3 hours. The apparent volume distribution was 140 liters. The FE was 0.65 and the FM was 0.35. صح؟ ومنين جبت هذول؟ من هذه statements. Fraction excreted unchanged in the urine was 65%, and the percentage eliminated as metabolite in the urine was 35%. هلا هذا كله بعد ما نعطينا دواء as what? IV bolus, right? مظبوط. This is after giving the drug intravenously. they gave us the values of the initial half-life, the VD, and the FE and the FM, right? So and these values are disposition parameters, right? All of these four values, they are disposition parameters. If I change the route from intravenous, the oral, will they be modified? And do they depend on the route? Disposition parameters. Disposition parameters, again, which are the initial half-life, the VD, the FE and FM, all of these are dosing route independent. And if you take them from the IV, you can apply them, the oral, right? We'll go to the oral. After giving the drug orally at 250 milligrams, okay, we got the absorption rate constant equal to 2.8 per hour. The intercept, which is equal to capital A here, is equal to what? To 1.66. This is at a dose of what? 250 milligrams. If I change the dose to 500, it will be doubled, right? And the fraction of the dose reaching the systemic circulation was 85.54%. This is equal to what? The absolute F, the absolute availability, right? So as I described before, the parameters that we got from intravenous bolus dosing, they can be applied also in the oral, because these are disposition parameters. They are dosing route independent. They are not affected by the dosing route, right? Right. First part of the question, the peak time and the peak plasma concentration following the administration of two types of doses or two dose strengths. The first one is the 250 milligrams. The second is 500 milligrams orally as a tablet. Okay. So the first thing that we need to do is to get the K, which is equal to 0.693 divided by the half-life divided by 3. That's equal to 0.231 per hour. That's the K. The T max is equal to natural log of Ka على Ka minus K, right? So it's equal to 0.971 hours. The CP max, this is the relation for the CP max, right? Again, we are asked to get the CP max after two doses. And if I change the dose from 250 to 500, we agreed that the T max will be the same, right? So we can use the same T max here for two doses, for the two dose strengths, right? So CP max is equal to Fx node multiplied with Ka على Vd divided by Ka minus K, Fuse minus Ka, or K for T max minus Use minus Ka for T max. The CP max after a dose of 250 milligrams. And the other thing, the question told us that the A, the capital A, is equal to dash 1.665. This is at the dose of 250. So we know that this whole thing here at the dose of 250 is equal to 1.665, right? And we know that the K is equal to 0.231, and the T max we calculated that to be 0.971, right? And we know that the Ka is equal to 2.8 per hour. Again, the T max is equal to 0.971. So the CP max at the dose of 250 milligrams is equal to dash 1.22, right? What about the dose of 500 milligrams? The only thing that we, as we mentioned before, that will be modified is what? The intercept. That will be double the intercept, right? So it will be 2 multiplied with 1.665. The T max is the same. The K is the same. The Ka is also the same, right? So that means that you are multiplying this C max by what? By 2. You double the dose from 250 to 500, right? Any questions until now? Any questions? Anything that's not clear? Okay, let's continue with the question. Determine the absorbable amount of the drug remaining at the site of administration that's equal to XA, okay, of the drug and the amount in the body at a time when the rate of absorption is equal to the rate of elimination. Well, what does this statement mean? متى بيكون rate of absorption يساوي rate of elimination? This is asking us to get these calculations at time equal to T max. So this is the definition of T max, right? And I can replace this whole thing by T equal to T max. Right? طيب طالب مننا نحسب ال XA الابزورببل اماونت. طيب نحسب الابزورببل اماونت XA max. اوكي والاماونت in the body at T equal also to T max. absorbable amount عباره عن XA node في US minus KA في T max، while XA node هي عباره عن F في دوز في US minus KA في T max. اوكي what's XA node? That's F which is equal to 0.8554 multiply with طبعا بدنا نحسب الموضوع هذا كله at dose of 500 right? So get a value of 500 here. It multiply with or e to power minus Ka, which is 2.8, or T max is equal to 0.971. That's equal to 28.2 milligrams. Again, this is absorbable amount, XA. Okay, this is not the XGI. This is equal to F multiplied with XGI. تمام؟ طبعا هاي الXA شو مالها؟ Is it constant over time or changes? It changes, right? It changes exponentially لأنه هاي relation شو مالها؟ Exponential, right? طيب, what about among the body? This is the same equation for the concentration in plasma, except that it's not divided by VD, right? So this is F multiplied with the dose multiplied with Ka divided by Ka minus K multiplied with e to power minus K F T minus e to power minus K F T. Again, we replace the T by T max, right? And the other way to do it, we know what CP max at those 100 of those of 1,500, right? That we just get. Multiply it with VD. If you multiply the CP max by VD, you'll get the X max at the same dose, right? So that's what we did. We multiplied the CP max, okay, by VD, 140 liters. We got a value of C max or X max of 341.6 milligrams. Tamam? Any questions for now? طيب, let's go to the third part. Determine the rate of absorption and rate of elimination at the peak time, okay, following the administration of two dose strengths اللي هم 250 و 500 milligrams. بده يعني نحسب absorption rate و elimination rate. Where at the peak time. اللي هم at the peak time شو مالهم؟ Absorption rate and elimination rate, they are equal. So which means that I can calculate one of them and say that the other one is equal to it. I can do it both ways. I can calculate the elimination rate and then say the absorption rate is equal to elimination rate, or I can calculate the absorption rate and say that the elimination rate is equal to the elimination rate. Either way will work, right? طبعا this depends on the parameters that you have. If you have the elimination parameters, then you calculate the elimination rate, صح? And if you have the absorption parameters, then you calculate the absorption rate. تمام؟ طيب, let's go to and do the calculations first at a dose of 250 milligrams at the peak. So the absorption rate is equal to Ka multiplied with Xa, okay, at T equal to T max. That's Ka multiplied with F multiplied with X multiplied with e to the power minus Ka to T max. تمام? This is the absorption rate. So the absorption rate constant 2.8. The F is equal to 0.8554. The dose is 250 milligrams and multiply with e to the power minus Ka multiply with T max, right? You plug in the values, you'll get an absorption rate equal to 39.45. What's the elimination rate? It's also equal to 39.45. This is at a dose of 250 milligrams. Now, we need also do the calculation at a dose of 500 milligrams, right? And at a dose of 500 milligrams, what should we do? Multiply the absorption rate first by 2. And if the absorption rate is doubled, also the elimination rate will be doubled. ليش؟ لأنه absorption rate will be equal to the elimination rate at the same dose. مظبوط? So basically, simply, what can you do? Just multiply this value here by 2. That will give you an absorption rate of 78.9 milligrams per hour, which is also equivalent to mean the elimination rate. Got it? Any questions? أنا نحكي عن موضوع الفليب فلوب كاينت. شو يعني flip flop كاينت اللي حكينا؟ What does it mean? Elimination rate is faster than the absorption rate, which means that the absorption is a slow or fast process. It's a slow process. When can the absorption rate be a slow process? Now, what causes the absorption rate to be slow? A formulation, for example, if you have a sustained release, okay, usually sustained release formulas, they have a slow rate of release, right? Which will be associated with slow rate of absorption, right? So this happens when you have a sustained release formulation, not a delayed release. Okay, it happens when you have a sustained release. Can you differentiate between delayed and sustained? You know what's the difference? But it starts from time zero, right? Like the anterior coated tablet. Okay. Exactly. So this happens when you have a sustained release, not a delayed release. If you have a delayed release, we'll talk about something else that's called the lag time. Okay. But a sustained release will be associated with the flip-flop kinetic. Also, some route of administration, like for example, the subcutaneous route of administration, usually it can be associated with flip-flop kinetic because the absorption from subcutaneous route usually is slower compared مثلا مع الاورال. اوكي؟ خصوصا اذا كان بيعتمد على الليمفاتيك سيركوليشن. بنعرف الليمفاتيك سيركوليشن شو مالها؟ It's a slower circulation مقارنة مع مين؟ مع البلد circulation. If your formulation is given subcutaneously and it depends on the lymphatic route, okay, you will have also a slow absorption that can cause flip-flop condition. تمام؟ طيب. So we agreed that this happens when you have either a slow release or a slow absorption. طبعا ليش slow release؟ لأنه حكينا قبل مرة for drug to be absorbed it need to be released and dissolved. صح؟ So if you have a rate limiting step of release, that will delay, not delay, that will be make the process of absorption slower. Okay, because of the slow rate of release. Right. So in our case, in case of flip-flop kinetic, we have K much larger than the Ka. The first thing that we need to talk about is the slopes. The slower process is the what? The Ka. So the terminal slope is you get the Ka, and from the residual line you can get the K. Using using the method of residuals that we have seen before. تمام? This is the first thing. Assume that we have this example. We have two drugs. One that has an absorption rate constant equal to 5, and the K emission rate constant equal to 2, and the other drug that has exactly the opposite values. It has a Ka equal to 2 and a K equal to 5. Okay? The first thing, what about the Tmax? Will they have the same Tmax or different Tmax values? Why? Because they have exactly the opposite values, right? The Tmax only depends on what? K and Ka. Now let's look at this. Tmax. I'll assume that this -1 is not there. Okay? Tmax is equal to natural log Ka divided by K divided by Ka minus K. Right? And what if I multiply the numerator and denominator by -1? This is like multiplying with 1. So this is -1. You take it to inside to the natural log, that will take the reciprocal, right? So this will be equal to natural log of K divided by Ka, right? And if we multiply -1 with this is like K minus Ka, right? Which is in our case applies to this example, right? Because we have exactly the opposite values of K and Ka. It doesn't make a difference whether the Ka is equal to 5 and K equal to 2 or the opposite. In both cases, you will get the same value of Tmax as it's shown here. We have the same Tmax, and we have shown this mathematically. And if you have flip-flop kinetic, you'll use the same equation for CP. The same equation applies, right? You have flip-flop kinetic. K is smaller than Ka, right? Or larger often than Ka, right? So this difference here will have what? A negative value, right? This difference, because K is small or larger than Ka, this difference will result in a negative value. But also, as we mentioned before, if you have a normal kinetics, we said that usually this term is larger than this, right? You have a normal kinetic. But if you have flip-flop kinetic, it will be the opposite. This term will be larger than this. So also this will have this subtraction will result in a negative value. Now you are multiplying a negative with a negative. That will give you a positive. As we mentioned before, the concentration needs always to be or to have a positive value. A concentration cannot have negative value. So likewise, the time, all of the pK parameters. Actually, in this course, you cannot have negative values. If you have anything negative in this course, and that is a sign that you have something error or you have something make mistake in your calculations. Okay? In this course, you cannot have negative values. You cannot have negative time. You cannot have negative concentration or negative pK parameters. All of them, they should have positive values. Now, going back to this relationship, we said that this only happens when you have a slow absorption, which can happen when you have, for example, sustained release formulation or certain routes of administration like the subcutaneous route for formulation that depends on the lymphatic absorption, which is a slow process. Okay, we said that the Tmax is the same. What about the Cmax? Which one will have a higher Cmax? If you have a normal kinetics or flip-flop, it's obvious. Why? Because in case of normal kinetics, you have a higher absorption and a lower elimination. But in case of flip-flop kinetic, you have a lower absorption but a higher elimination, right? Which will result in a lower Cmax. What about the area under the curve? It's also be the same, right? The flip-flop kinetic will have a lower area under the curve or compared to the normal kinetics. But how to know that you have a normal kinetics or flip-flop kinetics? And how do we make a decision that we have a normal kinetics or flip-flop kinetics? I assume that you have this data. You have done the calculations. You got a rate constant from the terminal part. You got a rate constant from the residual line. But how do you know that the one that you got from the terminal phase is an elimination rate constant or an absorption rate constant, and the same for the residual line constant? How do you know? ها؟ طيب واحد أكبر من الثاني بس هلا واحد أكبر من الثاني you don't know. واحد أكبر ممكن يكون الابsorption rate constant وبالتالي you have normal kinetic، أو بيكون elimination rate constant وبالتالي you have flip-flop kinetic. Yes, that's how to make a decision. هلا يعني usually you to make decisions about يعني using assumptions. You have to have a certain clue or a certain proof that you have either this case or this or that. Right? Okay. Let me remind you that you have a previous chapter that's IV bolus. But with IV bolus, you can get what? The K or the Ka. To give the drug intervention, you get the K. So you are sure that the parameter that you get from the IV is what? Is the K. So this is for sure, so there is no doubt, right? Now you have an IV data. From that you get the K. Then you go and compare that K to the terminal slope K. If it's the same, that means you have normal kinetics, huh? But it's high. If it's higher, okay, that means that you have flip-flop kinetics, because we said that the residual line it has a higher slope مع مين؟ مع terminal phase. So again, you need to have two types of data. You need to have an IV data plus the extravascular data. That way you make your decision. If the slope from the IV is the same as the slope, terminal slope from the extravascular, that's a normal kind. It's different, then you have flip-flop. You got it? If you don't have IV data, you have no clue. Okay? If you don't have an IV data, you have no clue. Whether you have normal kind or flip-flop. Okay? Any questions? Let's stop here. So next time we talk about the lifetime. As I said before, I will continue this part in the next section on Sunday, inshallah. Okay? So you are required to at least go on the Microsoft Teams and see the video that I record there, or you can listen from now to the videos that I already posted on the email for that section. Okay? And that will be the last part of this chapter. Let's take the attendance. The name that I mentioned, you need to prepare your stuff from now. If I mention your name, please raise your hand and then leave the leave the class. Okay. This is section 6, right? And you know that our mid exam was changed to 17th of May, right? That doesn't mean it's cancelled. It just moved, right? So you have to study the material. بصراحة يعني your interaction today is not like last time. It was much better last time. So please make more efforts of this course. يعني at least يعني this part will be يعني or this chapter will be part of the mid exam, and maybe the part that's next to it, that's the bioavailability. Okay. هلا if it's not part of the mid, it will be part of the final. يعني nothing will be يعني cancelled. Okay.